So last time, we finished up this little model problem where we had two atoms that we brought close together, close enough so that the wave functions could overlap. And then when you do that, you get this off-diagonal matrix element, these guys here, which basically couple the two states. So when the wave functions start to overlap, you can get these off-diagonal matrix elements that come from doing this integral here. And once that happens, then the energies, the way you phrase it, is the states couple. And if they couple, if those matrix elements exist, then this is always going to be what happens. The energies are going to move apart, and you're going to get lower energy and a higher energy. You're going to get, well, in this case, what looked like a bonding and anti-bonding orbital. So we drew the energies like this over here, showing what happens. So the energies just become your initial energy, epsilon 0, or maybe slightly shifted. We call this epsilon 0 tilde, which we really didn't care about that small shift. And in this case, since the atoms are the same, it would be the same shift for both, so it's just sort of a rigid shift of the whole system, which we aren't concerned about. But the qualitative thing that we are interested in is this splitting that occurs, and that's they split by basically 2T, 2 times the magnitude of T, where T is this coupling matrix element. So you get these two new states, or two energies, epsilon 0 plus T, epsilon 0 minus T. And we said that if you're just thinking that there's one electron shared between them, that electron would go into the lowest orbital, and the highest one would become unoccupied. And that made people a little uneasy, since both hydrogens, of course, have an electron. So what really happens is then you have to think about spin, which we won't think about for a number of weeks. But what happens is that you have the same Hamiltonian, like if you have this same 2 by 2 Hamiltonian, you'll have one for the upspin and the same thing for the downspin. If there's no spin-orbit coupling, if there's nothing related to spin in your Hamiltonian, the energies are going to be the same for up and down spin, which means that what you're going to get is both of those electrons are going to be sitting in that lower bonding orbital. So before you brought them together, you had one electron here and another electron here. I'll just draw the spins arbitrarily. After they bond, after they come together and bond, you're going to get both spins occupying the lower orbital, and that is your covalent bond. Yeah.
Are these energies negative or no? Is that not something I can say? Because I was working on the...
Negative with respect to what?
I was just working on the assignment, and I got negative numbers, and I'm wondering if that's something I can...
Well, T is negative, so yeah, they're probably... I mean, yeah, I maybe do we put in like real numbers at some point? I can't remember. I haven't. Remind me to talk about the assignment before the lecture, so like 10 minutes before.
Okay.
It's time. Someone remind me, because I get so excited I'll forget. But yeah, all the energies are in fact negative because the T's are negative. All the parameters you see in textbooks are negative. Usually it's referenced with respect to the vacuum, so all the bound states, of course, are going to be negative with respect to the vacuum energy. Okay, so for those of you who are feeling uncomfortable about one electron, so if you worry about spin, then you really have exactly sort of what you would see in some elementary textbook. You're going to have your two electrons sitting in the lowest state that are your bonding orbital. Okay. So in this little 2 by 2 matrix, we already calculated the eigenenergies as E plus and E minus, And then we went ahead and calculated the eigenvectors, which would be these column vectors here. And I made it more complicated than necessary. If you just immediately take t to be real, and t is negative, then this is like a plus t and a minus t, and so the eigenvector is going to be 1, 1. So somewhere here, 1, 1 means we just have, that's the coefficient for S1 and S2. So 1 times S1 plus 1 times S2 is going to be your bonding orbital, and if you want to make it normalized, you divide by the square root of 2. And for the antibonding one, well, this is t is negative. Negative magnitude of t is also negative. So then C1 and C2 have got to be 1 and negative 1 to make this thing 0. And you get your antibonding orbital over here. And then we drew, I think, a little simple picture of your bonding orbital. This guy, your lower energy one, and your higher energy one, which has a null right in between, right down the center between the two atoms. And then I backed up and showed how to go from your standard form for Schrodinger's equation that you see in your first textbook, some differential equation, and how to turn this into a matrix equation. Into this final form, some n by n matrix H down here acting on some column vector of C's. And these are the C's that weight your wave function. So this was a little abstract, doing it this way. Let me start a new, brand new one. Okay. So I'm going to do that same thing about turning Schrodinger's equation into a matrix equation just one more time. It's not that we really, go through the mechanics. We just make use of it, and from about after this lecture, we'll just be writing down matrices and solving matrix equations for eigenvectors and eigenvalues without much fuss. But it's good to understand sort of what underlies that. But before I do that, let me just show how what we've just learned about two-state systems is very, very general. It doesn't just have to do with molecules or bringing two atoms together, but you see it in other systems that perhaps, at first sight might not look like they have anything to do with what we were just talking about. And one of those systems is quantum wells in a semiconductor. Do you all know what a quantum well is in a semiconductor? Yes? Yes? Quantum well? Ring a bell? Quantum well. Okay, good. So in a semiconductor, if you draw the conduction and valence band in some heterostructure, this would be the conduction band, and this would be the valence band. And so basically what you've done is you've grown with molecular beam epitaxy some what they call heterostructure with a wide band gap and a narrow band gap. So here you would have, some band gap of one material, and here's the band gap of your second material that you've grown. And so you get these quantum wells here. Let's look at the conduction band. Just focus on the conduction band. So this looks like a little quantum well for electrons, and your lowest bound state here would have a wave function that looks something like that. It would be symmetric in the middle of that quantum well, and we could represent that abstractly as just an eigenstate of your quantum well. H times this state is just whatever that energy is times that state. That would be your fundamental state. And then I could grow some more material, grow a lot of material, and then I could repeat this thing somewhere over here. So another quantum well over here. And if they're far apart, in this region you have exponential decay of the wave function here because it's in the band gap. They won't feel each other because the wave function being exponentially suppressed in those regions. So if they're far apart, it's like your two atoms that are far apart, the wave functions essentially do not overlap. The wave function will be zero or exponentially negligible. But now if I bring these things together, and since let's say they're identical quantum wells, you grew them the same width, the same material, so these two energies are identical. Okay, so you have two degenerate states, just like we started off with our two identical atoms and two degenerate states. And then if I bring these quantum wells close together, now I have a system that looks like this. I'll just focus on the conduction band. Say with a narrow wide gap region between them, like that. Then what's going to happen is now the wave functions are going to tunnel right through that thin barrier. They're going to overlap. And I'm going to create some kind of matrix element between them. And the energies are going to do exactly what we just saw. You'll have a fundamental mode like this. It'll be symmetric. The sum of the two. And the upper mode will be anti-symmetric. It'll be like this. Like this. And so this would be our epsilon 0 plus t, so magnitude d, and epsilon 0 minus t down here. And it looks exactly like we just went through. You've got the anti-symmetric one, the higher energy one, which has the form of an anti-bonding state, and the lower one, which is symmetric, which has the same form as our bonding state. This always happens when you bring two states together. It doesn't have to just be in our atoms or in a molecule. It works equally well for quantum wells or any other kind of quantum systems you can think of where you bring two states initially far apart, close enough so their wave functions start to overlap so that you get a non-zero matrix element. The only reason it's not going to happen is if for some reason the wave functions are such that they are there's some sort of symmetry involved where even though spatially they overlap, when you do the integral you get zero. So you do the integral with the Hamiltonian, so there's some symmetry between the wave functions and the Hamiltonian. So even though the wave functions are overlapping, you get zero due to some symmetries, and then nothing will happen. You won't have that off diagonal. T will be zero, and you won't split the degeneracy. But in general, whenever the wave functions start to overlap, you will get something. And this is going to be what happens. Okay, so, and I guess the other thing is that this splitting that you're seeing is also, I don't know how many of you have heard of the Rabi frequency. So this splitting that we're looking at is also related to the Rabi frequency. And that would be, in this case, I got to get a frequency, I guess, T over radian frequency or just frequency. So the radian frequency omega would just be T over h bar. Right? T has units of energy. It's a matrix element of the Hamiltonian. H bar has units of energy times seconds. So the units of T over h bar is just 1 over seconds, which is our radian frequency. So what that means is if I were to put an electron in physically so it's localized, say, in this well, if I were to start with an electron sitting in this well, right, to get it sitting only in that well, it means the initial state, psi 0, is a linear combination of these two eigenstates. It's the sum of these two eigenstates, because if I take the sum of these two eigenstates, this part will cancel, right? Because one is the negative of the other. So then I end up with an electron sitting only in well number 1, if it's sitting in a linear combination of the eigenstates. So if I start off with an initial condition like that, what's going to happen is that this electron is going to oscillate spatially back and forth between the two wells. And that oscillation frequency is this Rabi frequency, which is this magnitude of T over h bar. So it's also related to some sort of time dependence of the evolution of your system if you do not start off in an eigenstate of the system. Right, if you do not start off in an eigenstate, and they actually did this experiment a couple decades ago, where they were able to excite an electron in one well, and then let the system relax, and because now you have charge that's oscillating spatially, it's like a little oscillating dipole moment, they could actually measure sort of a small AC signal coming out of that, and it would last for a few femtoseconds and then decay away, because if you're radiating, right, a signal, it means your power is coming out of that, which means that this state has to decay into an eigenstate. Otherwise, you'd have some kind of infinite, energy source. All right, so that's this coupling, this very general thing about what happens when you bring two states together. And before we go into the next problem, going from two states to an infinite line of states, I want to go through this concept of turning Schrodinger's equation into a matrix equation. Just a slightly different point of view. Again, we're going to start off with a basis, and you can happily think of this as your a set of localized atomic orbitals. So we have some set of these localized orbitals, and then we can represent any wave function as a linear combination of these atomic orbitals. So that's the way we represent any wave function. That's our basis. We're going to represent. So, and there's actually, in band structure theory, there's something called LCAO, which stands for linear combination of atomic orbitals. So you can think of the type of calculations we are doing as LCAO, linear combination of atomic orbitals. And the C sub I can in general be a complex number. And now we go to our eigenvalue equation, where we have our Hamiltonian, and I'll just represent it as an operator with a little hat on it, acting on my wave function psi is equal to E times psi, where E is just a number. And then wherever I see psi, I put in this sum over I. And so I have, and leave a little space on the left. So then I'm going to have H. I'll move my sum out here. Sum I, UI, and CI. Right, C is just a number, I can move it around, is equal E times this same sum. All right, all I did was replace psi with this sum. And then I'm going to hit this whole thing, just like we did last time, on the left with uj, right? Which means multiply and integrate. Right? Wherever you see these inner product, it's really an integral in space. So now I have sum I uj h ui ci is E sum I uj ui ci. And this was just our Kronecker delta function over here. Right? It's 1 when I equals j and 0 otherwise. This is just our Hamiltonian matrix element, H, J, I. And so the right-hand side just becomes ECJ, and the left-hand side just becomes sum I HJICI, which is our eigenvalue equation for these complex number C's. And again, if we write that out like we did last time in sort of normal matrix form, you would just have your matrix H acting on your column vector of C's, C1 dot 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 to Cn is equal to E C1 to Cn. And that's the eigenvalue problem that you send off to MATLAB to get your eigenvalues and eigenvectors. So if you have n orbitals, n is going to be an n by n matrix, Hermitian. H is an n by n matrix, which is Hermitian. And if it's Hermitian, you're going to get n eigenvalues and n eigenvectors. And they'll all be unique as long as there's no degeneracies. And these eigenvectors can serve as a basis. So you can use the eigenvectors of your Hamiltonian as a basis. It's called a diagonal basis. We said we could choose the atomic orbital basis. Well, once you've diagonalized your Hamiltonian, which means you've calculated the eigenvectors, you could use that basis also. And then you have what's called a diagonal basis, because in the basis of the eigenvectors, the Hamiltonian is a diagonal matrix, and the diagonal elements are just the eigenvalues, your eigenenergies. Okay, this is, from now on, this is, we're going to choose a basis, we're going to calculate the matrix elements of H, and we're going to solve for the eigenvalues and eigenvectors. So this is just sort of the underlying concept of how you go from what you've seen before to what we're going to be doing now. Okay, so we've done the two-state problem to death. Let's move on to a linear chain, which will be our first crystal. A linear chain, periodically placed atoms. I've got a linear chain of atoms, all lined up in a row. Uniform spacing, same atom, repeated over and over again in a 1D chain. And I'm going to label them like this: -3, -2, -1, 0, 1, 2, 3. And we're going to be looking, just like we did with our two atoms, we're going to be calculating matrix elements. This chain is essentially infinite. After a very long length L, you would apply periodic boundary conditions, but in the limit, you always let that L go to infinity. We're going to be considering nearest neighbor matrix elements only. So it means, and this will become more clear as we actually do it, if I'm considering atoms 0 and 1, I'm only going to be calculating the matrix element due to those two wave functions, S0 and S1. I'm only going to consider the potential of atoms 0 and 1. That's what nearest neighbor matrix elements mean. So this is what they call a nearest neighbor tight binding model, which is very common. And now let's go ahead and construct the matrix elements of the Hamiltonian. I guess before that we have to mention, so the basis is going to be the same basis we did with our two-state, our two-atom system, except now the number of atoms is essentially infinite, so the basis will be the same s orbitals, one s orbital on each atom. So that's our basis, and in this basis we construct the matrix elements of H. So again, starting with a diagonal matrix element. So S0 means the S atom the s orbital on atom 0. And I guess we go through the same procedure we went through before. We're going to get, I'm only considering nearest neighbor, the potentials of the nearest neighbors. So what would I get? I would get, for the potential of U0, I'm just going to get, I guess, E0. And then I'm going to get some contribution to the potential of, I guess, U minus 1 and U plus 1. So the potential of atom negative 1 plus the potential of atom plus 1. And these potentials are the same Coulomb. Everything's the same atoms we had before. Except before we only had 2 of them. Now we have a chain of them. So same atoms we just did. Now we're just doing a whole chain of them. And so, these potentials are negative. So this is just going to give me some shift, my initial. And since all the atoms in the chain are identical, it'll be the same shift for all the atoms. And I don't really care about a rigid shift. And the rigid shift is not what concerns me. It's all the off-diagonal stuff that's going to be interesting. And so that's it. Every diagonal matrix element, I could have just, so to generalize that, this would be SI, H, SI. So every diagonal matrix element is going to be the same, right? Because all the atoms are the same. Now let's look at the off-diagonal matrix elements. So now our Hamiltonian, we've got the potential from all the atoms, I. And that's what I need to take the matrix element of. So I'm looking at, again, something like S0, H, S1. And since this is just exactly the same as the 2-atom problem we just did, because as we said in this nearest neighbor model, here's 1, 0, minus 1, plus 1. When I'm taking the matrix element of S0 and S1, I'm only going to consider the potential on atoms 0 and 1. Because this wave function is localized over here, this wave function is localized over here, so by the time I get to atom negative 1, for example, over here, this wave function is strongly decayed. The wave function S1 is strongly decayed by the time it gets over here. And so the contribution due to the potential on atom negative 1 will be much smaller than the contribution to the potential on atom 0 and 1. And so that's sort of the concept behind this nearest neighbor model. These are also called two-center integrals for obvious reasons, because you're only taking into account 2 atomic sites. Right? These matrix elements are integrals, and these are called two-center integrals. Okay, and since we're only taking into account the potential that everything looks exactly like what we just did, so this is equal to, we just did this problem for our two atoms all alone. So it becomes identical to what we had before, S0, U1 plus U2 over 2, or U0, sorry, U0 plus U1 over 2, S1. Going through the same steps, exactly the same steps we went through last time. When I'm assuming all the orbitals are orthonormal, just like we did last time. And this would be your two-center integral. And this is, just like last time, this is your t, so really nothing has changed. So this is also, just like we had last time, this is your t. Same t as last time. It's going to be your t I plus 1, coupling nearest neighbors for all I, because again, every atom is the same. So this is the nearest neighbor matrix element between all nearest neighbors. So this I plus 1 is just, to be very clear, just our SI. UI plus 1. And now if we want to write down, well, the problem is, this Hamiltonian is infinite, but we can sort of schematically write down what we're looking at. So if I want to write down in matrix vector form what we're talking about here for our eigenvalue equation that we're looking at, because at the end of the day, we need something that we can solve. It would look like this. So all the diagonal elements, okay, there'd be your E0 tildes. I'm going to ignore tildes again. Just like so every 2 by 2 block, it looked exactly like what we had before. And since the t's are real, I'm not going to bother with the complex conjugate. So each 2 by 2 block is the same, but then the problem is this then is infinite. So it just goes on and on. Each row has 3 terms in it, t, epsilon, 0, t. And it just keeps on going. Dot, 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 dot. On both sides. And this would be multiplying your column vector, which is also infinite, e times the same column vector. So that's what we're looking at. And because it's a system that's infinite and just keeps repeating, another system like that is the vacuum, and we know the solution for that is in the form of a plane wave. So I'm going to just write down the solution and show that it is a solution, and then show what kind of band structure it's going to give us for our 1D crystal, which means what is the relationship between the energy and K. So the solution, our solution wave function, has this form. Label it by K, because you have one for each K, which is really a continuous variable. We have our normalization, where this is the number of, in this case, the number of atoms in your chain, which at the end you let go to infinity, but it's for normalization purposes. Sum over all atoms, your basis orbital, times e to the I, k, n. A, well, I guess I forgot to mention, A is what you would call the lattice spacing. So if you go back to our initial, A is, if you think of this as a crystal, A is your lattice spacing. And this is just our C sub n, right? Our complex number. We said we could write any wave function as a linear combination of the atomic orbitals, and here we've just done it, and weighted by some complex number. This is our complex number, e to the I k n a. And so, if you've heard of the concept of like the envelope function and the underlying block, the thing that gets repeated, the periodic part, and the envelope. This is your envelope, this e to the I k n a. This is the thing, we'll talk about Bloch's theorem later. This is the thing that gets repeated on every unit cell. This is periodic in the lattice. And if you've ever run into Bloch's theorem before, it says if you have a periodic potential, the eigenstate has a periodic part weighted by a phase factor e to the I kx. And so this is the form that we're seeing for this eigenstate. It's in a discrete form because we're working on a lattice, right? So instead of e to the I kx, I have e to the I k NA, but this NA, that really is our position, right? That is the center position of each atom N. I said NA, N times A, where A is your lattice constant, right? That is the x coordinate of each atom. Okay, so we put this form, so these are our C's, right? These are our CNs that we're going to put in our column vector. And then we're going to multiply this column vector times this matrix. And every row of this matrix is identical, right? Just shifted over by 1, T epsilon 0 T. All the rows, each row gets shifted over by 1 as I go down. And so for any row n, we get, when we do this matrix vector multiplication for that, multiplying that column vector times choose your row, we'll call it row n, you get T times E to the I Ka times n minus 1 plus epsilon 0 times E to the I K A N plus T E to the I K A N plus 1. So for any row n, that's where you're going to get when you do that matrix vector multiplication. And that equals, on the right-hand side, E times E to the I K A N, because this is row n and that's C sub n, right? That is C sub n. Okay, I see some puzzled looks. We good? It's the matrix vector vector matrix multiplication. What's the puzzlement? Okay, well, if you believe that line, and I hope you do, then as you can see, every term in it has an e to the I K A N, which I can factor out. So I'll factor out the e, common e to the I K A N term. And I'm left with T e to the minus I Ka plus epsilon 0 plus T times e to the plus I Ka is equal to E times this same phase factor e to the I K A N. And so I can cancel this common phase factor on both sides. And now you see I have E as a function of K. Right? We were looking for, this is going to give me our E-K relationship, which is what you call your band structure. E is a function of K. So that sum of the phase factors is just going to give me a 2 cosine Ka, right? So I'm going to get epsilon 0 plus 2t cosine Ka is equal to the energy. So for each K, for each wave vector, that's what its energy is. So you're labeling your states by K, and for each state K, that's its energy. Again, the T is a negative number, so let me write that as E is epsilon 0 minus 2 magnitude of T cosine Ka. And if you were to plot that, often people using such a simple model would let epsilon 0 just be 0, since you're not worried about the, exactly what the energy is. you shift the whole thing, so just let epsilon, like, we'll see this when we do graphene. Let epsilon 0 be 0, and then it's centered around 0, and it goes from minus 2t to plus 2t. It's a periodic function, right? Because the cosine is periodic, so it goes from from k maximum pi over a to minus pi over a, and you just get this cosine band. Okay, you get a cosine band going from minus 2t to plus 2t. The energy 0 is arbitrary, and often we like the bottom of the band to be at 0. So we shift the whole thing up so that, your bottom of the band is sitting at 0. And so it basically represents, I don't know if you've heard this sort of concept, the kinetic energy of the electron. So right when it's at the bottom of the band, its kinetic energy is 0. As you start going above the band edge, your kinetic energy increases, and E becomes synonymous with the kinetic energy of the electron. And so if you do that, you just shift your function vertically, you have E, and this is a final form. It's 2 magnitude of t times the quantity 1 minus cosine Ka. So we just shifted our function up by 2t, so that its minimum is now at 0. And so this final form that you should keep in the back of your mind, minus pi over a to pi over a maximum at 4t, and you just get your cosine band sitting in there, centered at 0. And it's periodic, so we could keep plotting it, but it just is going to repeat itself. Like all band structures, it's periodic. And this, going from minus pi over a to pi over a, is your Brillouin zone. So in K-space, this region from minus pi over a to pi over a is your Brillouin zone. So this is, in this case, it's a 1D, because we started off with a 1D crystal. So we have a 1D Brillouin zone. And what you have is a band structure. We've just calculated the band structure of a 1D tight binding chain. A band structure of a 1D tight binding chain. Okay, another thing that we call this is a dispersion relation. It relates energy to the wave vector. And one dispersion relationship that you've already come across before is that of light. And light is a linear relationship where E is equal to h bar c k for light. The wave vector of the photon is related to its energy by that relationship for a photon. For an electron in a band, it's going to look something more like this. For one, it's going to be periodic. Right? So for an electron in a band, it's going to, first of all, it's going to be periodic for our electron in the band, and it's going to have a finite band width. Right? This thing has both a bottom and a top, right? It ends at 0. I mean, the bottom is at 0, the top is at 4t, and there's nothing else. That's it. Whereas light just goes goes off to infinity, never stops. And we'll see that in the parabolic model we're going to talk about in a second. Okay, so A finite bandwidth, that's probably something you're not used to thinking about. This is what's called the bandwidth. People are familiar with the band gap, but since bandwidth is this, the width of the band. The band gap is the gap between two bands. Here in this model, we only have one band, so there's no band gap. There's only one band to worry about. Okay. So let's compare this solution that we just calculated for a 1D crystal with one s orbital on each atom. Let's compare that to the solution that arises from the effective mass model. Okay, so what is the effective mass model? That is, in the effective mass model, you look up in some reference book for the semiconductor of interest and you'll find numbers for the, quote, effective mass. It's a reduced mass. And it'll be some value for the mass of the electron that is, say, often, depending on your semiconductor, less than the mass of the electron in the vacuum. So, for example, in, say, gallium arsenide, for the electron, it's 0.067 M0, where M0 is the actual mass of an electron in the vacuum. And so in the effective mass model, all you do is you take your differential Schrodinger's equation and you replace the true mass of the electron with this effective mass. So we can go ahead and do that. So in that case, you have your minus h bar squared over 2m star d squared dx squared. Again, we'll just do 1d, d squared dx squared psi equals e psi. And we know, this is just the equation for an electron that frees in the vacuum. And so the solution is psi. I'm going to use the same type of normalization we just used, 1 over root L, where L would be the length, which you've let go to infinity, e to the I kx. That would be your solution. And if you put this plane wave back into Schrodinger's equation up there, you take the second derivative, you just pull out a negative k squared, right? So if I put this back up in for my psi, take the second derivative, all I do is pull out a negative k squared. And so I immediately get, and then I cancel the e to the I kx on both sides of the equation, and I immediately get that e is equal to h bar squared k squared over 2m star. And this is my dispersion relationship for the effective mass equation, and it's a parabolic dispersion. It's just a parabola. It has no top. Just like what we were talking about with the photon, it has no periodicity. And it just goes up forever. So it's not periodic, and there's no top to the band. So the question is, what's the relationship between these two dispersions, the one we just calculated with the cosine band and this one, because so often people just use this as a starting point to do some analytical calculation or gain intuition. But before I answer that question, I'm going to do something, I guess I'll explicitly show you what the relationship is. And to do that, I'm going to solve this effective mass equation up there at the top left numerically, as if you didn't know how to solve it like this. You wanted to solve it numerically using a finite difference approach, right? Just like you would solve any differential equation on the computer. Let's apply a finite difference to this differential operator and see what happens. So we're going to solve this, solve the effective mass equation, and solve the effective by finite difference with using the same discretization length of A. Okay, we're going to discretize this, the same discretization length A as we had for our lattice constant. And so we have to discretize that second order derivative, d squared dx squared. How many of you have done that before? Finite differences? One, maybe. Okay, so here's how you derive that. So we all know sort of the fundamental definition of, the first derivative of a function. So I've got here are my sites, just like before. I'm going to discretize it on this, discrete set of sites, 0, -1, 1, 2, etc., with a discretization length of A. So the function will be known for these values that lie on our discrete points, -1, 0, 1, 2, etc. So if I want the derivative of f at x equal to 0, I'm going to define some intermediate points, which we're not going to actually use, but they're just nice to have for the derivation. So halfway between 0 and -1, and halfway between 0 and 1. This derivative in discretized form would be, and this is a centered difference approach, it would be f of 1/2 minus f of -1/2 divided by A, the lattice constant. So it's this value here, f of -1/2 and f of 1/2. Take the difference, divide by A, and that would be the way I would get my derivative at site 0. Right? That's kind of just using what you learned about the it's called it says you can do it right, like a right difference, left difference. This would be centered difference. I think it's centered because I'm taking the value to the right and the left, taking the difference. So the difference is centered around the value that you're trying to calculate. Okay, so that's sort of tells you the algorithm to apply when you want to discretize a derivative. And now we just apply the same algorithm again to get the second derivative. So now I want d dx of this thing I just calculated, d dx f0. And so I just apply this to each term in that numerator. So the derivative of f to the 1/2 over here would just be f1 minus f0 over a, and I'm just going to put the a down here right away. I'll end up with an a squared term down here. f1 minus f0 over a, and then the derivative of f to the -1/2 would be f0 minus f of -1 over a, but I already have the a downstairs, right? I've just applied that algorithm again to each term. So it's sort of a, this defines how I take the sort of the DDX operator in finite difference form. This is what the DDX operator does to any f at any site. It takes the f halfway above, the f halfway below, takes the difference and divides by the distance. That's what how you define the operator on this discrete lattice. And then I just apply that definition again to get the second derivative. And then I combine my terms and I get f1 f1 minus 2f0 plus f negative 1 all over a squared. So that's the finite difference form of the second derivative on this discrete lattice. And so now the finite difference form of my Schrodinger's equation now becomes minus h bar squared over 2 m star a squared, and instead of f, this is my wave function now, psi for any atom n, I'm going to get psi n minus 1 minus 2 psi n plus psi n plus 1 is equal to E psi n. And if you look at that, it looks pretty much like our tight binding expression for equation for any row. I've got the center element n coupled to the term to the left of it and the term to the right of it. And now we just put in the solution. And now we put in the solution just like we did for the tight binding one, that psi n is equal to E to the I K A N. So you can immediately see this is an equation for what we called the envelope before, sort of the C's that multiplied the underlying basis states, those s orbitals. So this is an equation for the envelope, because these were the same CNs that we had before. And so if I put this form for psi into the equation above it, I'm going to get minus h bar squared over 2 m star a squared times, I'll immediately factor out, as we did before, the common e to the I K A N term, and then I'm going to have e to the minus I K A N minus 2 plus e to the I. Oh, I'm sorry, not K A N, just K A, and I factored out. That's e to the minus I K A minus 2 plus e to the I K A, and that's equal to e times this common phase factor, e to the I K A N, and again we'll cancel out the common phase factors from both sides. And so we get from our finite difference solution that, let's see, this term becomes, so this thing in the brackets is minus 2 times 1 minus cosine Ka So negative 2 plus 2 cosine Ka. That's the thing in the brackets, right? And so we finally get that E is equal to h bar squared over m star a squared times 1 minus cosine Ka. And if you compare this expression to the one we got from our tight binding model, we had there that E was 2 magnitude T times 1 minus cosine Ka. Okay, so, I mean, the form is identical, and this allows us to make the connection between these two models. So just comparing and setting equivalent, it means that my T is equal to h bar squared over 2 m star a squared, which makes the connection between the two models. And so this tight binding model with one orbital per basis gives you the exact same solution as just starting off with your usual effective mass equation and just using a finite difference approach to solve it, right? Because now, because we put it on this discrete lattice, did finite difference, now this also, we introduced a periodicity, the same periodicity of A as A, and we introduced a finite bandwidth of 4t, or in this case, the bandwidth is going to be, I guess, 2 times this value here. So we can look at some limits. Let's look at the limit as, what is that? K goes to 0 or A goes to 0. So if we look at E in the limit that either K goes to 0 or A goes to 0. So A is your lattice spacing or your discretization length. Okay, so what's going to happen? Well, cosine Ka in the limit of very small Ka just becomes, so in that limit, cosine Ka just becomes 1/2. One plus this, K squared A squared plus 1. Right, that's what your cosine Ka term becomes as Ka goes to 0. And so your dispersion relationship was h bar squared over m star a squared times 1 minus cosine Ka. I had 1 minus cosine Ka, so I have 1 minus 1, this is a minus sign here, plus 1/2 K squared A squared. 1 minus 1 plus 1/2. Because cosine Ka goes to 1 minus 1/2 K squared A squared. And so these terms cancel out, of course. And so that's equal to, I get my 1/2, h bar squared K squared over 2 m star, because A squared cancels. which brings me back, that was the original parabolic, right? That's our old parabolic dispersion from the effective mass model before we discretized it. So in the limit of small k, in the limit of small k, if we go back and compare these two things, so for small k, which means I'm very close to k equals 0, right here in the center, I have my parabolic model. Oh, that's terrible drawing. And my cosine, I should have used different colors. So this is my cosine band, this is my parabolic band, my k-squared band. So right down near k equals 0, and the limit for small k, they're going to be the same. They have the same curvature, the same second derivative. So in almost all cases, this parabolic dispersion that you get from the effective mass model is good for, all right, this is the energy axis, this is the k-axis. So it's good for low energies near the band edge. Remember in the very beginning, we said, in your device courses, all you talk about is like EC and EV. And now we're talking about the dispersion, the EK relationship that goes, above the top of the band. But right near the band edge, like in your Streetman course, this parabolic dispersion, this parabolic relationship is good within some small energy range near the band edge. And this is sort of mathematically showing the limit of how one goes back and forth into the other.